unloaded the circuit, the DC-DC converter, draws about 6 milliamps, like you can see over there. A little bit more, see 6.1 milliamps. But that, of course, is with absolutely no load on the DC-DC converter, right? So this current will shoot up as soon as I will put a load over the output, of course, of the DC converter. Now, if I read correctly, it's not designed to source more than, say, well, 20-25 milliamps, yeah, which is perfect for the B plus of the Crown radio. We don't need much more than that. So yeah, well, there you go. 6.1 unloaded, 6.1 milliamps. Okay, so this asks for a little bit of explanation. So I built a little device now, which is over there on the breadboard, and which actually is nothing more, you could say, than a variable power supply, but which I fixed at a at a fixed voltage. Okay, and the explanation is here on the schematic I drew. Now, before I go on, just remember this: you are working here with high voltages. Although the currents are rather low in this device, they can still hurt you quite badly. Yeah, so especially if you have a pacemaker or something like that. So if you're going to make something like this, you better beware there's high voltage on this, and you should take all the necessary precautions. Okay, that's it for the safety bit. Now the explanation. Right, so our plan was to use a DC-DC converter, which is this little device here, and use it as a power source for a variable power supply, which is here, which actually is not variable but is fixed at a certain output voltage. Okay, now in essence a DC-DC converter is a little bit like this. Let me show you. Okay, so the DC-DC converter is in fact what's called in the books a voltage multiplier, and in effect it's really nothing more than an oscillator which oscillates at a certain frequency. I think this one works at around, well, let's say 4 kilohertz, give or take a few hertz, and it sends the AC voltage it generates, which is low AC, okay, into a small transformer, which is this little thing here. Okay, now the transformer has on the other side a lot more windings, which means that it generates a lot more voltage. Now the voltage, of course, is still AC. So what they do on the DC-DC converter, and which by the way is an up converter, they charge up several capacitors in conjunction or with the help of a few diodes, and the charge which resides on each of the capacitors in the end is being added up. So say you have 200 volts here, well then you would get 200 volts on this one, 200 volts on this one, 200 volts on the C3, and on the last one yet another 200 volts. But since they're all in series, yeah, you add up the voltages and you get, in effect, 800 volts at the output. Okay, so that's how it works. Now, funnily enough, we're absolutely not interested in this part of the DC-DC converter. What we are interested in is the high AC, which is on the secondary of the small transformer. Okay, and so we go on here. So the AC that comes out of the DC-DC converter, which is, if I'm not mistaken, somewhere around 100 volts, okay, it can vary a bit. It was reasonably high, but then there was no load on the converter, so I would say with load the output voltage is around about 100 volts AC. Now we put that AC voltage into a bridge rectifier, which we build ourselves with 4 1N4007 diodes, which you see underneath the large electrolytic you see over here. Okay, so let's see if I can make the image a bit sharper. There you go. Okay, so you see those 4 little black things? Well, those are the rectifiers. Right. So the output of the bridge rectifier is I would say around 100 volts, say 110 volts, something like that. Now obviously there's quite a bit of noise on that DC that we just created, especially since this is a high frequency oscillator in essence, and that's something we really don't want. We don't want any AC on top of the DC, or it will translate into a heavy buzzing of the radio. Okay, so we put a filter capacitor over it, and I noticed that a 6.8 gives a satisfactory result. Now the makers of the DC-DC converter specify that one should not go over 10 microfarads. So and I guess that's to do with the amount of current a capacitor draws when charging. Okay, because that little transformer you see over here really can't take a lot of current. Right, so here at the output of the filter capacitor we have nice smooth DC. And now, since the DC is too high, remember we need only about 67.5 volts DC, we need to lower it. And what I'm going to use to do that is a voltage regulator, which is in fact an LM317. Okay, and you see the pinout here. Okay, so don't make the mistake a lot of people make to think that in a logical way, you know, the left pin is in, the right pin is out, and the middle pin is adjustment. No, no, no. This is the exact pinout of the LM317. So if you hook it up differently, it will burn. Okay, right. So we input the high DC into the in pin of the LM, and then we output the voltage here, which ultimately will go into our little radio, and we also put a resistor bridge over that, or I should say a voltage divider bridge. Okay, and part of that voltage which is tapped off between the resistors is used to set the LM output voltage. Okay, now one very important detail with this setup: you absolutely need to put a Zener diode of not more than 39 volts, yeah, between the output and the input pin, and you need to place it like it's drawn. Okay, so the cathode of the Zener diode must go to the input pin and the anode to the output pin. The reason is that this is what is called in engineer parlance a floating power supply. Okay, so normally the LM can only take roughly anywhere between 30 and 40 volts between input and output of its pins. Okay, not more, or it will burn. But if you let it float, as they call it, and the floating is done thanks to this little Zener diode, it really doesn't matter what voltage you have at the input and what voltage you have at the output, as long as the difference in voltage doesn't exceed 39 volts. Okay, so the Zener diode you see here is really essential. Right, so since we set it with these resistors to a maximum drop of voltage, what we get at the output is 66 volts. Okay, so if we assume that the output of the bridge is 110 volts, then the output is about 66 volts. Okay, so it all depends on the quality of the resistors and their heat susceptibility and all that, but really I measured it and I got around about 66 volts, give or take a few hundred millivolts. Okay, which is perfect. You might say it's a tad low, but really that's okay. So what we're going to do next is I'm going to build or transfer all these parts you see here onto a tiny PCB, and then I'm going to hook it up to the DC-DC converter, and we're going to test it out. Right, I hooked up the whole radio chassis, as it were, to my power supply, which is all of this. Let me give you an overview. So right here you have my high voltage power supply. Okay, granted it's still not finished, but it works, and I built a temporary filament voltage supply, which is really nothing more than 2 AA batteries, which I soldered together, and which I'm going to use to well, to light up the filaments. Okay, now the problem is I had already a quick go at powering up the radio, well, at least what I hoped it would be a power up, but the radio does nothing. And when I say it does nothing, I really mean nothing, not a sound. So obviously there's quite a bit more going on than well, than I initially thought there would be. The very first thing I'm going to measure is whether in fact I do have filament continuity, because well, if the tubes don't get heated via the filament battery, which is in fact those two soldered batteries I just showed you, then it's no use pumping high voltage through the radio. You see, the tubes won't react in any sort of way, and the fact that I'm not getting any kind of sound, and I mean really zero, yeah, seems to me to point to a break in the circuitry. Well, okay, so if you look at the schematic of the radio, you see that all the filaments are actually connected parallel to each other. Okay, so I need to figure out whether in fact there is a break somewhere by which the power for the filaments just doesn't reach the filaments. So that's what I'm going to do now. Alright, a few observations. First of all, I'm measuring the current the filaments draw when the radio is on. And the battery is, or the batteries I should say, already, well, have already served quite a bit. So the current has dropped a bit, but originally the radio drew about 125 milliamps filament current, which is a lot of current for such a small radio. And then, since I still didn't hear any sound coming from the radio, okay, I put the local oscillator onto the scope. And the local oscillator works perfectly, in fact. So when I tune the variable capacitor to change the frequency, you can see the local oscillator follows the variable capacitor quite well. Okay, so in fact the local oscillator is running perfectly, I would say. If you measure it from where I'm measuring it, you know, which is where, let me take a pointer, which is where the scope is hanging from, right here. So you've got two variable capacitors on the tuning capacitor. You have what is called, let me see, one is called the C1 and the other is C2. Let me see. Okay, yeah, right. So the variable cap to which I attached my oscilloscope probe is called the capacitor 2, whereas the one that comes from the antenna, the wire that from the antenna that runs into it, is capacitor 1. Okay, so perfect. So yeah, I know the local oscillator works, but I'm not getting a single sound out of the radio, not even some crackling. So there must be something going on with the amplification of the high frequency signal, or maybe rather the demodulation of the high frequency signal. So I need to look for a problem somewhere down the line in one of the IFs, so either this one or that one. Now I've got one luck, which is that as far as I can tell, the capacitors which are attached to the coils are probably located outside of the IF cans and not built within. But if they are, well, then we might have a big problem. Because have you seen how small these cans are? Look at my fingers. Compare it to the IF cans. I mean, these IF cans are tiny, really tiny. So if I would have to remove capacitors inside of those, well, then it's not my birthday yet. I had to rule out whether my power supply, the one I built, was the cause of any malfunctioning of the radio or not. And so I hooked up the radio to my lab power supply, and I'm churning out as much voltage as I can from it, which is about 32 volts, and it seems to be enough to make the local oscillator function, so that's fine. But still, no sound from the speaker, absolutely none. Now with my probe, I test the output that goes to the speaker, which is here, and all I get is a loud buzzing. Okay, now there seems to be a hint of reception at the background, but since my ears are so bad and my lab power supply is creating so much background noise, I can't really tell. The fact is, the speaker, well, as far as I can tell, doesn't give a peep, not even a tiny sound. So I would tend to say that the trouble is probably located either in the IF or the output tube, which is the 3S4. Okay, so well, I ruled out any trouble might be coming from my power supply, so let's try to detect other problems. Now, before I end the video, I might also add that some resistors don't look too fresh, I would say. Is that proof that something's bad? Not necessarily, but these carbon resistors are known to fail by themselves over the years, okay? So it's quite possible that one of the resistors or one of the capacitors might have turned bad as well. So what I'm going to do actually now that I know the local oscillator works, is to concentrate myself on measuring all the resistances in the circuitry, and if they measure okay, then move on to measuring the capacitors. Now, I said at the beginning of the video that I would try to keep all the original parts, but it looks more and more like it that I will be forced to replace at least a few components in the radio if I'm ever going to make it work, which might also include the original electrolytic, which you see over there. Okay, so yeah, well, now we start measuring everything, which is, you might say, the slightly tedious part of it.